Okay, so this is the first lesson in our Unit 10 unit on probability and statistics. And so today is just going to be an introduction to what is basically probability. You may have seen some of these questions before in a previous math class, so this is going to be somewhat of a review, but just more sort of just an introduction into what we're going to be doing for this unit. So first of all, we're going to deal with theoretical probabilities, experimental probabilities, and then as well as finding sample spaces. Now, none of this should be terribly difficult, so hopefully we can get through this pretty efficiently. So a probability experiment. Okay, just if you were to do what are the odds of drawing a king in a deck of cards or something like that. So a probability experiment is an action or trial that has varying results. So a probability experiment is something that when you are doing the probability or you're doing the experiment, there are different things that could come up. Like in a deck of cards, you could get a 9, you could get a 5, you could get a king or queen. Those are varying results. Whereas if I were looking at if I just had cards of just queens and what's the odds of getting a queen, that's not really a probability experiment. There has to be varying results. The outcomes are the possible results of a probability experiment. I can write. These are the outcomes. So these are the possible things that could happen. Like in our deck of cards, I could get a king, I could get a 9, I could get an ace, so those would be all the outcomes. It would be a list of all of the possible things that could happen. The sample space would be the set of all possible outcomes. So we'll start pretty easy here, some pretty basic ones that aren't too crazy. And the one that you always sort of see is flipping a coin and rolling a die. This is something that if you see this on any standardized test or anything like that with probability, you see always flipping a coin and rolling a die. So how we figure out the sample space or the total of all possible outcomes, we start with the first part. So if we're going to flip a coin, what are the two things, what are the things that can happen? Well, you could get heads or tails. So the coin will do first, and your two possible things that can happen are heads and tails. Now from that, if I go to roll a 6-sided die, I could roll heads, and then when I go to roll the die, because it's a 6-sided die, there are 1, 2, 3, 4, 5, 6 possible outcomes. I could get a 1, a 2, a 3, a 4, a 5, and a 6. Or I could flip the coin and get tails and then roll the die and get a 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So your sample space is going to be the sum of all past possible outcomes. I can get heads and a 1, heads and a 2, heads and a 3, heads and a 4, heads and a 5, and heads 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in this particular example, there are 12 possible outcomes. And that would be our sample space. Okay. The second one is a cafe's lunch special is a hamburger meal. It comes with a choice of a beverage, soda or tea, and a choice of salad, garden, potato, or bean. So when we do this, the first choice obviously is the hamburger meal. Everybody's going to start at the hamburger meal, so we'll start there. But once you get a hamburger meal, now you have a choice of a beverage, a soda or a tea. So from here, I can do one of two things. I can get a soda or I can get a tea. And then after that, I can have a choice of a salad, garden, potato, or bean. So I could get the hamburger meal with a soda, but then get a garden, potato, or bean salad. Garden, potato, or bean salad. Or I can get the hamburger meal with tea and get a garden, potato, and bean. So again, the sample space is just a sum of all of these possibilities. So 1, 2, 3, 4, 5, 6. So for this one, there are 6 possible ways to do your order at this cafe. Okay. All right. Theoretical probabilities. These are the probabilities that you always think about. So like these are the probabilities that, if I have a spinner that has 4 pieces to it, there's a spinner with 4 pieces, the probability of landing on one of the pieces would be 1/4. That's theoretical. Now obviously that may be different from the actual experiment, but theoretically, because if there are 4 things on a spinner, I would have a chance of getting 1 out of 4 on that spinner. So that's what theoretical probabilities are. It is a measure of the likelihood or chance that an event will occur. Your probability is always going to be a number between 0 and 1, because it's always going to be a fraction, or here you can see it as a fraction, a decimal, or a percent. And so because probabilities are always something out of something, it's always going to be you could see it as a fraction or a decimal as a percent. You'll see me convert everything to percents. I like percents. You'll see why in a little bit. Percents are just easier to work with when you're finding other things as well. So I like to convert everything to a percent. It just, like I said, it makes things easier when moving forward. So the number between 0 and 1, for me, most likely it'll be a percent. So obviously you have between 0 and 0 would be like there is no possible way that something can happen. So, and then 1 would be like the probability of it happening. It is going to happen. It absolutely will happen. There's a 100% chance of it happening. So that's what 0 and 1 mean. So theoretical probability is when first of all, you can use it when all outcomes are equally likely. Like it's random. People get confused by this. All outcomes are equally likely, but you're like, well, wait a minute, that's not equal. What this means here is that your things are random. Like when I go to find the probability of getting a 9 or something like that in a deck of cards, I'm not any likely to choose a different card. They're all random. So, and you'll see what I mean a little bit later. So how we write this is it's P of A. So the probability of some event is written as P of A equals the number of favorable, or the outcomes that you're looking for. I'm sorry, I'm like going off the page here. the number of favorable outcomes over the number of total outcomes. Okay. And so you'll see what I mean here in a second. So here's an example. The probability of randomly, keyword randomly, that's what we can use theoretical probability, randomly selecting the following in one draw from a jar containing 8 blue marbles, 5 red marbles, and 2 orange marbles. The first thing that you have to do is figure out, well, what are the total amount of outcomes? I could choose an orange. I could choose the other orange. I could choose a red. I can choose the other red. I can choose another red. And so basically we just add all these up. So 8 plus 5 plus 2 is a total of 15 marbles. I'm like running out of the room here, sorry. So there are 15 possible marbles I can choose. Okay, so the probability of choosing an orange marble, you would take the total amount of orange marbles, so the probability of, and that's O, not 0, probability of orange is 2 out of the total of 15 marbles. Now I'm going to go ahead and convert that to a percent. 2 divided by 15 is 0.1333 or 13.3%. The probability of choosing a blue marble, since there are 8 blue marbles, would be 8 out of the total of 15 marbles, which, if I convert that to a percent, is 0.5333 or 53.3%. In red, the probability of a red marble, since there are 5, is 5 out of 15. That's 1/3, so 33.3%. So that's theoretical probability. The odds of getting marbles, you always see marbles. Marbles are a very common example of this. On the back, here's another example. A student taking a quiz randomly guesses the answers to 4 true or false questions. What is the probability that the student gets 2 correct? Okay, so let's say you're blind, you're closing your eyes, and you're just circling random answers to 4 true or false questions, and you're like, okay, what are the odds that I get 2 of them right? Okay, so what we have to do first of all, so step 1 will be finding your sample space. In other words, find the total number of possible outcomes. So we can do this like in a table. So if I do the number correct, so let's say, so there are 4, this is a keyword here, there's 4 true or false questions. So if I were to get none of them correct, then the only thing that's going to happen is that all of them are incorrect. So each question is incorrect. Question 1, 2, 3, and 4. But if I get 1 correct, the specific problem I get correct can change. So I could get the first one correct and the last 3 incorrect. I could get the second one correct and the rest incorrect. I could get the third one correct and the rest incorrect, or I could get the last one correct. So just getting 1 correct, I could get any one of the problems correct. Now what about 2 correct? I'll have to write kind of small here. I didn't really leave myself a lot of room. So I could get the first 2 correct. Sorry if this is really small. Let me zoom in here. So I could get the first 2 correct. I could get the first and the third correct. I could get the first and the last correct. I could get the middle 2 correct. I could get the second and the last one correct, I'm going to have to make another one here, make another row. I could get the last two correct also. So that goes with that one. And then 3 correct. I could get the first 3 correct. I could get the first 2 and the last one correct. I could get the first one correct and then the last 2 correct, or I could get the last 3 correct. This goes with that one. There you go. And then if I were to get all 4 correct, this one's easy because then all 4 of them are correct. So now that we have all the possible outcomes of getting 0 correct, 1 correct, 2 correct, 3 correct, 4 correct, now we have all the possible, this is our sample space. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So for this, there are 16 possible things that can happen. Now I can actually find the probability. So the probability was 2 correct. Well, here's all my examples of 2 correct. 1, 2, 3, 4, 5, 6. Which means that the probability is 6 out of 16. Or if I change that to a percent, 37.5%. It's not bad. 37.5% chance of getting two questions right. So if you were guessing, it's not that bad of odds. Okay, let's zoom out. Get out of here. Okay. So the probability of a complement, sort of confusing, but basically the probability of a complement is what's the probability that something won't happen. So the sum of the probabilities of all outcomes in a sample space is 1. Since if you were to add up all of the probabilities, they should equal 1, 100%, right? So you can find the probability of the complement by simply just subtracting from 1. So let me just finish here. A complement of an event consists of all outcomes that are not in A, is denoted by we call this A bar. You can think A bar. That's what it is. Basically, this is the probability that an event won't happen. That's usually what it is. So if we use the example up here with the test questions, the probability that I got, or that I wanted was, what's the probability of getting 2 correct? Well, I could flip that around and say, what is the probability of you not getting 2 correct? And that basically would just be all the other ones, or the difference of this from 100%. So this is 37.5. If I just subtract that from 100%, I'd get 62.5. So basically, there's a 37.5% that I get 2 correct, but a 62.5% that I don't get 2 correct. And so that's what a complement means. And we write that like this: P of A bar equals 1 minus the probability of an actual event. And you can think of it as like 100% instead of 100% minus the percent of the probability of an event happening. Now, we talked about theoretical probabilities. Theoretically, like if I flip a coin, I have a 50-50 chance. There's a 1 in 2 chance I'm going to get tails. And theoretically, if I were to flip a coin 50 times, 25 of them would be heads and 25 would be tails. But the real thing is, if I were to actually flip a coin 50 times, the likelihood of me actually getting 25 and 25 is not likely. Usually you get more one of the other, because in an experiment, sometimes things don't go like it's supposed to. So I might get like 37 tails and like 20, and 13 heads, but theoretically, because there's only two sides to a coin, the chance of getting them on one side or the other is 50-50. Now that's what we call theoretical. But experimental is when you actually perform an experiment and get different results. So an experimental probability is based on repeated trials of a probability experiment. And this can be found by just taking the number of successes over the number of trials. There's an of in there. Number of successes, number of trials. So here's an example. Here's that spinner problem. So each section of the spinner as shown has the same area. The spinner was spun 20 times. Okay, spinner spun 20 times. The table shows the results. For which color is the experimental probability of stopping on the color the same as the theoretical probability? So this is actually what we're trying to find here. Now, I know when I printed this out, it's black and white. On your notes, if you're split screening this and you're doing it on your notes, there are colors here, and I actually don't remember what colors are what. It actually doesn't matter, so I'm just going to label them: red, green, blue, yellow. It doesn't matter. There are supposed to be colors there. So when you spin the spinner, theoretically, since they're all four the same size and there's four sections to the spinner, theoretically landing on a green or a red or a blue or yellow should be 1/4 of the probability, or 25% chance. Landing on a green would be 25% chance. Red would be 25% chance, and blue and yellow would be 25% chance, theoretically. So first we find the theoretical, that's not how you spell theoretical probability, and that should be because there's four things and they're all the same size. The theoretical probability would be 1/4, or 25%. So what it's asking is which one of these colors actually came out to be the same as the theoretical probability. Now you might be able to guess it just by looking at it, but let's look at all of the examples. Experimental probability. So let's look at yellow. So the probability that came out with yellow is you got it 3 times. Now, okay, you spun it 20 times. So 3 out of 20 times it came up on yellow. Now that percent, if you convert it to a percent, it's 15%. The probability of getting blue is also 3 out of 20, which is also 15%. The probability of getting green is 9 out of 20. I mean, this is all experimental. This is what you actually got. 9 out of 20, which is 45%. And then the probability of getting red was 5 out of 20, or 25%. So it looks like red is the color that actually got the same as the theoretical probability. Okay, so since our theoretical is 25%, red looks like is the only one that sort of followed that. The other ones were a little bit more or a little bit less than theoretical. All right, last question here. In the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them have at least one pet. The types of pets these adults have are shown in the figure. What is the probability that a pet-owning adult, keyword pet-owning adult, is chosen at random, has a dog? Now, there's a bunch of stuff here, and the reason for really doing this type of problem is to really focus on information that is necessary. Because we are asking what is the probability that a pet-owning adult has a dog, The fact that they surveyed 2,184 adults and only 1,328 of them had at least one pet means that they surveyed just random people, and these are the ones that had pets. So if we're looking at the probability of a pet-owning adult having a dog, we don't actually need this number. It's not relevant. It's sort of a distractor. It's there to sort of throw you off. I don't actually need that value because this is the value of pet-owning adults. So when I'm looking at this, what's the probability that a pet-owning adult has a dog? Well, a dog has, so the probability of a dog is, well, 916 of them have dogs out of 1,328 people that have pets. And so when I do that, and I convert it to a percent, it's like 68 point whatever, but it rounds up to 69%. So 69% of U.S. adults with pets actually have a dog. And that is our introduction to probability.